without further ado, I'm going to invite our next speaker up. He works at Twitter, at scaling Git at Twitter. Some of you, who's heard of Twitter? Is anybody? Nobody's heard of Twitter. OK. It's sort of a social app. It's not big in France, so but it's quite big in the United States. So he's going to tell you all about how they scale Git at Twitter. So please welcome Will Bierbaum.
I am Will. I've been at Twitter for about 5 years. Yeah. I have worked previously on the front-end systems and the traffic management systems. And now I work on Git at Twitter. We've basically decided that it's really important to make Twitter a good place to work for developers. Source control was one of those areas where we were kind of lacking. We had some performance problems with Git in the past, and we decided to try to make it better. And I'll talk a little bit about large repositories and how Git interacts with those repositories, and the things that we've done specifically to make Git work better with large repositories. So Twitter now runs development of all of its services out of a single monolithic repository. It's one huge repository that used to be 3 somewhat large repositories. For better or worse, working in a single repository when you have a lot of services really allows us to, well, working in a single repository is the way that people prefer to develop software when faced with developing hundreds of services and dealing with thousands of build targets. In addition to being in a single repository at this point, we have a single build system that helps us build everything consistently. We have a lot of contributors who submit numerous changes every day. Quite a few of those people are beyond the offices, the walls of our San Francisco office. So we have a geographically diverse workforce, and that's something we need to take into account when we're trying to scale the SCM. We actually do use the normal canonical implementation of Git when we're working on code, but we do have a few optimizations that I'm going to discuss later. Yes, so this huge repository sounds like a bit of a mess, but there are some benefits. For instance, why would you put everything to one repository? Well, one thing is that it's visible. It's easier for people to find code if they're looking for it in one repository, while code search solutions that can target more than one repository obviously exist, and especially in GitHub and these kinds of things. For enterprises, they're not as fluent. So it's just simpler, instead of asking where the code, which repository of the code that I'm looking for is in, to have it all in one place. In addition, we run a single tool chain. So there's a single set of tools to build, test, and deploy, and operate the services that are developed in the repository. When people make improvements to those tools, everyone benefits because everything's on a single tool chain. We actually do rely quite a bit on IDL, interface definition language. So when operating many small services, which is very important to Twitter's architecture, even though they run in separate process spaces, they all get developed together. And this is because we'd like to totally minimize the amount of duplicate code there is. And beyond limiting that repetitive code, we rely heavily on the interface definition language and code generation to create classes that model data and encapsulate the service boundaries. So sharing code and IDL in a single repository gives us an easy way to keep our client and server code synchronized, and it ensures that the deployed software is compatible when it's running. So this is, in effect, we're trying to model what will happen in runtime in our repository. So when we're troubleshooting service issues in any environment, it's a lot easier to look at a single code base. It allows developers to mentally parse the delineation between services and these things much easier than if they were in separate code bases. so it's easier to understand the entire system. It's also easier to understand the impact and scope of changes that you make. So using a single build tool and repository has benefits for the planning aspect of coding. Since everything can be compiled together, it's easy to make a change and see what breaks, rather than having to submit changes to multiple repositories, build those repositories' code, and change the dependencies among them. We can just edit files, land the changes that might affect multiple systems, and do this all within a single commit, and then run the tests and see what's happened. So this makes refactoring a lot less arduous, and it also plays into encouraging principled interface design. And when you do have to make breaking changes, they're easier to coordinate with other people, since the code review and testing is all within one repository. So what's bad about having one big repository? Well, some common challenges with the larger repositories are that, some organizations have chosen to use sparse checkouts to control the number of files necessary to maintain the working copy. There are many objects required for the complete representation of an entire repository's history, and those occupy considerable storage resources. And great numbers of them can cause normal operations like git status to perform quite slowly. Tuning the file system only goes so far, and that's why people end up limiting the amount of history and possibly partitioning their repositories. One example of partitioning in a large repository that many people might be familiar with is what's done in the Android project. The maintainers of the Android project have chosen to partition their build tree into many smaller repositories, and then they use an external tool called repo to synchronize the projects that are at the top level. So there may be Android at the top level in the code that's part of that, but all the dependencies, such as libraries that are developed by third parties, are pulled in by a separate tool. And those are their own separate Git repositories. To us, using a tool such as repo that's in effect a secondary version control tool on top of Git just kind of feels not right, and it doesn't lead to a fluent experience. So going back to the Git core suite, there's a mechanism that we have in Git core called submodules, which, although they seem attractive in providing a way to partition these large projects into smaller repositories that might be easier to manage, the reality is that a lot of developers don't feel very comfortable with submodules, despite the fact that submodules have really improved a lot over the course of history of Git's development. So commands that you use in everyday Git, such as like add or commit, they don't recognize submodule boundaries very well. So if you have changes you make in a submodule and you're at the top level, you won't be able to actually add and make these commits in parallel. So this is one thing that large repositories allow us to do that isn't serviced very well by the submodule subsystem. So I'm going to talk about how we use Git at Twitter for a minute. We use Git in a very centralized way. And unfortunately, and I think this is the case for a lot of people, certainly people who use GitHub, we don't really benefit from the fact that it's a distributed version control system beyond the fact that it's good at managing merging patches. So for development of the services, we try to do it as close to master as possible, and we discourage maintaining long-running branches. The goal is to have as close as possible view of the entire system in a single version. Having everyone works against master limits the amount of coordination that's necessary between developers to make changes, and has a secondary effect of minimizing the number of conflicts developers have to resolve when they merge their changes. While there is a project-level ownership model in our code base, any developer is actually welcome to change any code. So this is one of the benefits that having a strong review model allows us to expose to people. Our topology is that we have a lot of read-only replicas that mirror changes from a highly available read-write server. As developers push changes, those changes are written through to the read-only cluster. In any given Git installation, it's likely that there are a lot of applications, for instance, continuous integration and tooling, that read data more than those that write to it. And so scaling out our read-only cluster has helped us meet the demand in the context of our read-heavy workload. We use reference repositories extensively when we're doing parallel test runs and these kinds of things, where you have many copies of a repository that need to be present on a machine when you are, but they don't actually necessarily need an entire clone themselves. So reference repositories, if you're not familiar, it allows you to have an entire object backing store with a separate working copy and a separate log and all these things. So while Git has pretty impressive performance in general, for large repositories, there are some places where performance could be improved. So when you're fetching or pushing changes, upload pack does this initial payload of all the references that you have in the repository on the server. And that takes a long time to transfer when you have a lot of references. And furthermore, the disk format of the references is kind of inefficient in general. So if there are a lot of changed branches and you haven't fetched for quite some time, you might run into some locking problems because of the fact that there are pretty low file descriptor limits on certain operating systems, particularly Mac OS X in its default configuration runs into these problems. So when you change references, you actually have to take a lock file for the reference, you have to check a lock file possibly for the packed refs, and so on. So when you have a lot of these, you might run into the file descriptor limit, transactions might fail, which is not great. Common commands like status and these commands also take quite a while sometimes in the presence of many objects and references, regardless of whether the repository is well packed. Garbage collection sucks in any form. Nobody really likes to see automatically packing the repository for optimum performance when they're trying to get work done, especially when you have millions of objects. And unfortunately, while there's been work done to background the garbage collection, there are some locking issues with it. So, what has Twitter done? We're experimenting with several changes to improve the performance of the repository. Our goal is to make performance of fetch, push, status, commit, and branch faster specifically, since these are the most commonly used commands. So to improve status performance, some people might be familiar with file alteration monitors. Facebook has actually put this into action in their Mercurial implementation, and they have developed a alteration monitor called Watchman that Mercurial consults to see which files have changed since the last time they asked. Or there are some other semantics, but largely this is the case. So when you're doing git status, one of the most expensive things is to make the system calls to do the statting to see which files have changed since last time. And Watchman alleviates that by pulling that all into the userland process. So this has a pretty pronounced effect on Mac OS X, which pretty much all of our developers use and pretty much every developer uses, since HFS Plus has pretty poor performance compared to Linux and ext4 when the default kernel configuration is used. We also have a new index format. The index tracks the state of files in Git, and we've adopted a faster hashing algorithm that uses native instructions that allows our index to perform a little bit better. So as I mentioned before, when you connect to the server, it sends you all these things that you probably already have. So as soon as the clients connect, they receive the list of references. In the context of large repositories with many references, the list can be huge. In our case, it's about 13 megabytes of raw data. And all this data has to be sent each time, despite the fact that there's only a small fraction of branches and tags that might have changed between fetches. To address sending this huge piece of data, we've started experimenting with having clients send a Bloom filter representing the present state of their references. So they hash everything together into a Bloom filter, send this to the server, and as the server is enumerating through the references that it has, it checks whether or not they're present, whether they're hits against the Bloom filter. It only sends references back that are misses. So basically, using this optimization, we're able to cut down the number of references we have to send back to pretty much a minimal number of them. And right now, we've implemented this as an optimization only in an HTTP header, because it's kind of a hack. But if we were going to formalize it, we'd like to put it into the Git metadata and put it in the protocol, possibly in the sideband. One of the other things that we've got is the most contentious thing. The fetch protocol is pretty expensive. When you're trying to locate objects to send back as a pack to a client, the amount of random I/O through compressed data that you have to do is pretty extreme. So this means that when you're actually fetching, it can take minutes to negotiate which data you actually want, and then the transfer time on top of that to get that data. So bitmap indices help in this area, but they're pretty computationally expensive to keep up to date for us, especially when they need to be repacked. And since we have a central deployment and pretty significant requirements to have the same data on multiple machines, what we've chosen to do is rephrase the fetch protocol completely. So basic information retrieval, combined with the fact that we've learned this through building a lot of serving systems, says that we should try to make what we're serving as close to, on the wire, as close to the disk representation as possible. And we realize this in our replication and fetch scheme using journals of commits and reference changes. This technique means that we have no computation on the server beyond a send file system call to relay the changes to clients. So how does this work? When people push to the server, to the right server, the objects are, all of our commits are serialized. We have a commit queue. So it only writes one commit at a time. That's an important part. We're going to take a global lock for each push in this case, instead of the normal reference level lock that Git takes. When you're pushing, you're generating an intermediate pack. And what we do is we hold on to that pack just through messing with the configuration variables a little bit to make sure that they don't get deleted or loosened as soon as they're received by the server. What we do is that we append these packs to a log structured journal file. The journals are regular files on the disk. They're named with monotonically increasing numbers, serial numbers. And we've got these set to somewhat small size limits to ease operation of dealing with these journals. After the pack is appended, we also append a record of which reference was modified. So you have the entire data necessary to extract all the changes, and to know which ref actually changed in this case. And these are saved to something called an extents file. So there are two files. There's the extents file, there's the journal file. If the clients are configured to use these journals, when they connect to the server, they attempt to retrieve the extents file. All the data in these files is append only. So this synchronization can actually be achieved purely by requesting the rest of the bytes beyond the length of the current extents file the client already downloaded or was provisioned with. I'll talk a little bit more about the client provisioning in this case later. So after they receive that data in the extents file, they know which parts of the journals have changed. They try to retrieve the journal or journals, and then they extract data from these. The way that they extract data is what we call replaying the transactions. So the packs and their indices are extracted from the journal. The refs are updated in batch through ref update after they're pre-processed to reduce the unnecessary number of transitions. For instance, mutations of a branch that are later deleted turn into deletions solely. And after this, they basically write how far into the extents log they've gotten so that they can remember next time where to start in the extents log. And to appease the garbage collector, and to prevent this proliferation of really tiny pack files that represent each individual transaction, we invoke another process that's like a repack that runs in the background and combines all the small pack files into a larger one. This kind of doesn't play well with the heuristics of pack files, but in practice, people end up doing full repacks often enough that this isn't much of a problem. So the fact that it's log structured gives us a few operational benefits. It's really cheap to serve thousands of clients off one machine. And the data they read is always going to be in their file system cache, pretty much. So all we're doing to give them the data they want is sending files and sending bytes over a wire. And since all the files are essentially dead on the disk, there's the possibility of introducing intermediate HTTP caches that understand range requests between the client and the server. This is useful in situations where you have geographic diversity because the round trips between San Francisco and, for instance, London or Paris are quite long, especially considering encrypted connections. So we can set up somewhat dumb proxies in far-off places that yield much better performance for the people that we're trying to serve changes to. So basically, without these journal fetches, our repository won't fetch at all. And this gives us a much more predictable runtime and is often faster than git fetch. There are some drawbacks. For instance, it requires a bit of care to operate this. Clients have to be configured properly. We have to maintain that they're configured properly, so we have an entire system to deal with that. And at present, instead of cloning using regular git clone, we have people fetch initial snapshots through BitTorrent, so that it doesn't take so long to actually extract all this stuff. For some users, fetching and replaying all the changes might be overkill, so you can use this on a per ref basis. You might have this set up so that master always gets journals, and then the rest of the branches are fetched from a differently configured remote where the journals aren't necessary. So you don't end up transferring everybody's branches along with the code that you're actually going to share. And finally, and this is the most important thing that people say, is that it doesn't support redaction. So if people push stuff that shouldn't be there, like private keys and stuff, we don't have any way to delete it. But realistically in Git, people could have already read those objects and have them on their local machine, and there's no way to actually enforce that objects are deleted on clients. So we feel like it's kind of a so what situation. Fixing that would be pretty easy, however. some of the other things we'd like to do in the future are work with the sparse and shallow repositories. This is especially similar the case that other people at Facebook, for instance, are experimenting with sparse repositories. We haven't gotten to that yet, but we'd like to. It would also be nice to have a storage abstraction that's a little more flexible than what's in Git right now. It's going to be really crucial to making future performance improvements possible. And I've started experimenting personally with an interface that mimics what's in libgit 2, that's loadable shared objects into regular Git, and kind of getting somewhere with that. And finally, using that pluggable storage, we'd like to possibly adopt a network-aware storage backend so that checkout becomes an online operation, but you're only fetching certain objects that you need. And we maintain that as your objects on disk essentially become a cache instead of a necessity. And with that, we do want to contribute stuff. We're not sure this stuff's right for everybody. We've never really wanted to maintain a fork. We kind of do right now. But if any of these optimizations appeal to people, and I think that possibly the ref mutation optimizations might, we'd love to work upstreaming those. And by design, we've tried to make all this stuff have a pretty small footprint in the code base where modifying existing programs is concerned. And integrating these changes should be pretty easy. All these optimizations are totally optional, and they're configured through, controlled through configuration. And with that, if anybody has any questions, I don't have that much time left, but if you have questions and you want to talk to me afterwards, that'll be fine. Thank you.
Oh, there's a question?
Oh, sorry. Yes. Does any of it make sense to upstream? I think that specifically the thing where we send the Bloom filter that indicates which branches need to come down is a huge optimization that could be upstreamed. The alteration monitor is a change that we tried to upstream, but other people were working on that at the same time in Git without any dependency outside of Git. There's a huge tendency to not want to take external dependencies, which is fine. But yeah, it would make sense to upstream a few of these changes. The journal isn't for everybody. It's great for situations where you have a huge repository and everybody's getting the same thing all the time, which is the case that we had. And it's also great for mirroring. It's much faster than using regular fetch mechanism for mirroring. But it might not make as much sense for everybody. I'd imagine that that can be separated out and sent as a contribution or as a separate extension to Git, such as what happens with Git Annex or these kinds of things. But it might never have a place in actual Git. And it's still possible to achieve these things in the scope of an extension. There aren't significant modifications necessary to make this happen. The only real modifications are to the tools that you use to fetch and pull, for instance. Cool. Thank you, guys.
Thanks, sir.
Thanks.